Surface and Canopy Layer Stories. I'm going to be your chair for the session. I'm Jorge Gonzalez from University of Albany in New York, USA. And we have almost a full session, and we're missing one speaker, no, one speaker,
The slides, yeah.
one presentation. But they tell me that we better stick to the time. So if this fellow doesn't show, then we will take time to have conversation about stuff. Yeah. So without any further delay, and my co-chair Henry, and I'm going to be sharing the first four. And he's going to help me out. So my voice almost going to it's not like crazy. All right, so Professor Dan Lee from Boston University, Massachusetts, is going to be the first speaker. Dan, thank you for coming.
Yeah. Okay. Thank you, Jorge, for the introduction, and thanks everyone for coming to this session. It's my great pleasure to kick off this session by talking to you about the impact of anthropogenic heat flux. I'm really just presenting on behalf of my postdoc, Linying Wang, who unfortunately could not be here. Before I started, I would like to acknowledge that this is part of the IM3 project funded by the Department of Energy in the US. The paper has come out about 3 weeks ago, so if you're interested in more details, you can read the paper, which is on Environmental Research Letters. So the motivation of this study is that there have been quite a lot of numeric studies trying to quantify the warming effects of anthropogenic heat flux. So in this incomplete list of the previous work, you can see that we have studied different regions across different countries using different numerical models in which they prescribe different magnitude and sometimes also different patterns of anthropogenic heat flux. And then, as you can imagine, they get different responses of urban temperature. So in this case, we argue that the temperature response itself may not be actually a good indicator to look at the physical processes because, as you can imagine, the magnitude of the warming effect of anthropogenic heat flux must be related to the magnitude of the anthropogenic heat flux itself. So instead, we argue that perhaps the quantity that we should look into is the sensitivity, which we define as the change of the canopy air temperature in the urban environment normalized by the magnitude of the anthropogenic heat flux that we inject into the numerical models. And if you do so, you can find that there's actually a better consistency across these different previous studies with the magnitude typically on the order of 0.01 Kelvin per watts per square meter, with some remaining variabilities. So now you can ask basically two questions. First, why is the sensitivity typically on this order of magnitude, 0.01, instead of 0.1 or instead of 10? Second, what are the physical processes that are actually responsible for the variability of this sensitivity that we see in studies? In particular, if you read closely these papers, you will find that this sensitivity tends to be stronger, for example, in winter than in the summer. Namely, if you put in the same amount of anthropogenic heat flux in the winter, you typically get a stronger warming effect. Okay, I'm sure we can come up with different ways to address these two questions, but the way we're going to do it is to build a sort of forcing feedback type of framework based on the energy balance idea. So in this case, we write an energy balance for urban canopy air, which is also the approach that you take in numerical models that sort of parameterize the urban environment. We treat, for example, the urban canopy air as the air that is trapped inside of this urban canyon, and we assume that the canopy air has no heat capacity, so whatever the heat goes into the control volume has to be balanced by the heat coming out of the control volume. If you think of the energy into the control volume is the anthropogenic heat flux, then the energy coming out of the control volume are two convective heat fluxes that is driven by the temperature difference between the canopy air and the air above the canopy. You can think of it as the bottom of that large-scale atmosphere or atmospheric boundary layer. And then the other convective flux from the canopy air to the surface. Of course, we can use then the bulk formulation that is widely used in meteorology to parameterize this canopy convective fluxes, but with two different convective heat transfer efficiencies, with the subscript A and S indicate the to the atmosphere or to the surface respectively. If you look at this energy balance equation, close not enough, you will realize that this energy balance equation is nothing but actually just a linear function of the canopy air temperature on the right-hand side of the equation. So to make my notation a bit easier, I'm going to just basically write the anthropogenic heat flux as some slope of this linear function number 0 multiplied by the canopy air temperature plus some intercept C0. Well, if you reformulate the original equation, the number 0 will be related to the convective heat transfer efficiency, while C0 will have this formula. Well, to better understand this energy balance idea, perhaps we can use a graph. Here I'm plotting the total fluxes on both sides of the equations as a function of the canopy air temperature. So you can assume that the anthropogenic heat flux is a force into the system, so it's not a function of the canopy air temperature. So it's represented by just a flat black line. Since the right-hand side equation is just a linear function of the canopy air temperature, it's represented by this red line, which is a linear function of the canopy air temperature. Now you can see that the canopy air temperature has to be at this crossing point because it's only at this crossing point that the left-hand side equation is equal to the right-hand side of the equation. Namely, you are in an energy balance state. Okay, with this type of thinking, you can start to say, okay, what if we increase the anthropogenic heat flux? Well, the way you increase the anthropogenic heat flux on this graph is you bring up the black line, and you immediately see that you get a new crossing point, even if you assume the red line stays where it is, and you can do the math a bit more rigorously, right? You can actually immediately see that the change of the canopy air temperature is nothing but the change of the anthropogenic heat flux normalized by the slope of this red line, which represents the convective heat transfer efficiency number 0. Well, this is what I call the basic no feedback scenario. This basically assumes that as you put in anthropogenic heat flux into the system, the red line, which sort of represents how the system dissipates the energy, stays where it is. You only increase the canopy air temperature because you want to dissipate or you want to balance the anthropogenic heat flux using convective heat transfer. Well, you can imagine that as the system is going to evolve as you put in the anthropogenic heat flux. For example, what if this red line does not stay where it is? It changes slope into this blue line. Now you can see that the warming signal that you get, which was the red arrow, now becomes this blue arrow. So effectively, using the language of climate feedback, you introduce a negative feedback, which damps the original warming signal from the anthropogenic heat flux. Okay, let's think through this whole process a little bit more carefully using this, sort of forcing feedback language or thinking that I've kind of like alluded to through this figure. We know the forcing to this problem is you add anthropogenic heat flux into the numeric model. The no feedback scenario is basically you increase the canopy air temperature because that's the only way you convect more heat somewhere else in order to preserve the energy balance. But as this process goes on, you can imagine the system is going to respond. For example, as you convect the heat to the surface from the canopy air, the surface temperature is going to increase, and then as the surface temperature increases, the canopy air further increase. So that's perhaps a positive feedback. And then the heat conductances were also changed, right? As you can imagine. The canopy air, the temperature above the canopy, the large-scale atmosphere, will also change its temperature, but we're going to exclude that since in this study, we're going to mostly focus on the canopy layer. Although you can, of course, include that in the extended model. And how do we formulate this problem in a more mathematical fashion? I only have 3 equations, so let me walk you through them. The first equation basically says that as you change the anthropogenic heat flux, the right-hand side of the equation has to be changed in the same way, otherwise the system is not balanced. And I'm going to denote the right-hand side of the equation as minus R. It's just some notation. Now you can see that the sensitivity that we're looking for, which is on the left-hand side of the equation, is related to the change of the canopy air temperature normalized or divided by minus dot R from the first equation. And you can put the change of the canopy air temperature into the denominator. Now you have something that is often called the feedback parameter in the climate change literature. And then you can use the so-called chain rule to expand this total feedback parameter using into the partial derivative, which is the baseline scenario where everything else stays the same. And then, of course, you have the surface temperature feedback, you have the feedback from the heat conductances. So that's what we are going to use to diagnose whatever simulations that we produce, to understand what are the processes cause the effectiveness of the anthropogenic heat flux on the warming. Okay, so what you will be seeing here is the only result slide that I'm going to show. That is the simulations that we did were used the so-called community land model, which has an urban parameterization. We did it over the entire continent at a resolution of about 1/8 degrees, or about 12 kilometers. And everything you see are the climate feedback parameters. On the left is the summer, on the right is the winter. Everything has been averaged over the diurnal cycle over 3 months in the summer and winter season, and then averaged over 20 years in the historic climate from 1991 to 2010. You probably can't see much of the spatial variability, which is okay. So I'm going to ask you to really focus on the value that is showing on the upper right, which is the median value across the corners. One thing that stands out, if you look at the first row, which is the total feedback parameter, is that its value is about 120 to 110 watts per square meter per Kelvin with a minus sign. And one way to interpret this climate feedback parameter is that you can change it to a sensitivity. The sensitivity is just the inverse of the climate feedback parameter with a minus sign taken out. So this immediately tells you that why in previous studies we always see a sensitivity that is about 0.01 Kelvin per watts per square meter, because the total feedback parameter is about 100 watts per square meter per Kelvin. So now we've already explained half of what we wanted to explain. Most of the sensitivity is coming from the baseline scenario. So you don't even need to consider a lot of the feedbacks in the canopy layer. Once you know the baseline scenario, that is on the order of, again, about 100 minus 100 watts per square meter per Kelvin, you know half of the story. But now let's see the feedbacks that we put into the whole story. The surface temperature feedback is a positive one, as we probably would have imagined. As the surface temperature increased, the canopy air temperature further increased. The heat conductance between the canopy, or more heat convective efficiency between the canopy air and the air above the canopy is a negative one, because as you increase the anthropogenic heat flux, the stratification of the canopy layer becomes more unstable, so the heat tends to be more easily convected into the large scale atmosphere. So the warming within the canopy is somewhat damped. This is actually the blue curve change to the red curve change to blue curve scenario. So that's a negative feedback. What's interesting when you think of the seasonal variability is that in the summer, the positive feedback and the negative feedback nearly cancel each other, with negligible contribution from the other conductance between the canopy and the surface, which is because that heat conductance is not really affected by the thermal stratification in the canopy layer. So no contribution. But if you look at the winter time, the negative feedback from the heat conductance or convective heat transfer efficiency is much more reduced in terms of its magnitude. And hence, the positive feedback from the surface temperature wins over the negative feedback, which gives you the increased sensitivity of the canopy air temperature to the anthropogenic heat flux. This tells you that without considering the feedbacks from the surface temperature, the heat conductances in the canopy layer, we will not be able to understand the seasonal variability of this sensitivity. At the end, I want to just tell you that this whole force and feedback thinking has been also applied to study other problems. These are the two studies that are also done by my postdoc, Linying Wang. If you're interested in this, feel free to give these papers a read. With that, I'll stop and happy to take any questions. Thank you.
Yeah, we have time for one or two questions. And if you can please use the microphone so then we can move around the only. Yeah.
Interesting talk. I'm concerned that you didn't consider the latent heat flux in this study, right?
No.
So what's the consideration of that?
Was the same question out for you?
You can use the same thinking for latent heat flux. You just write the budget for the humidity within the canyon. If you're talking about I'm assuming you're talking about the anthropogenic latent heat flux. It's the same type of thinking. As you go in, as you inject the latent heat flux into the canopy layer, your humidity start to change, and then there will be responses, right?
It probably will not be linear, no?
Uh, it will not be linear if you start to include condensation or phase change. Otherwise, the convective part is fairly linear. Amir.
Thanks, Dan. I wonder if the inclusion of roof surface temperature would change the result of your analysis because roof temperatures oscillate at a much larger amplitude.
The the good question. The in when I showed the schematic, I only showed one surface temperature, but in reality, in the formulation of the COM urban, the roof surface temperature is part of the surface temperature. So there are like five different surfaces, and they all interact with the canopy layer. So effectively, you have to consider that you basically instead of one surface, you actually have five of them altogether. Well, in the GFDR model, then the roof surface does not connect to the canopy layer. But then, we can argue about which model in terms of this structure is correct. But if the roof is connected to the canopy air temperature directly, then you have to link that into the formulation directly.
Okay. Any other questions for Professor Lin? Please.
Hi, Professor Lee. Thanks for your interesting presentations. I have two questions. My first question is, will the impact of anthropogenic heat on the air temperature differ in different seasons and different time of the day? And my second question is, because if we're introducing the air conditioning into the building, the condition will be totally different because it helps to transfer the indoor heat gain, indoor cooling load to the outdoor, and it will significantly affect the impact of anthropogenic on air temperatures. So have you considered the AC?
So the answer to the first question is quite straightforward. We looked at also the diurnal variations in the paper. I didn't show here, but yes, the diurnal variation can be studied using the same approach. Mostly it's related to the stratification, and how the stratification is affected by adding more anthropogenic flux. The second question about the air conditioning, I'm not sure exactly what you were asking.
It seems to me that you incorporated the energy exchange from the surfaces. Keep in mind that there's a lot of additional energy coming from the used air conditioning, both
Oh.
latent and sensible.
The anthropogenic heat flux is treated as a forcing from the perspective of the canopy air. In this work, the anthropogenic heat flux can come from the building. It's just the source of the anthropogenic heat flux is not particularly specified in this problem. It can be from transportation, from building energy consumption. So that is not a problem in this thinking.
Thank you.
We actually have a little bit more time. There is any other questions for Professor Lee? Because the second speaker is not here. Are you okay with?
Yeah.
Just one small question, Natalie. Because you talked about the sensitivity, the anthropogenic heat, and the air temperature, right? Which level of the air temperature?
That's again a great question. Even for modelers, me included, I don't think I understand what the canopy air temperature actually represents in the real world. It's a fictitious temperature that you use to link the